The dot product is a scalar product. The dot product gives you a scalar, a number. The cross product gives you a vector. It's a vector product, not a scalar product. The cross product is going to give you a vector that is at right angles to both the two vectors you're putting in. So, I'm going to write it and then I'm going to explain it. You remember the dot product for comparison. A dot B is mod A, mod B, cos theta, right? The cross product is A cross B. That's why it was important. I kept saying write a dot for this one because this one's a cross instead. And it is A, B, sine theta, n hat.
You going to explain why?
Yes. I'm giving the people who are writing notes, it should be you then, enough time to write it. So then we can talk about it. Where, as usual, now I've got other pens in front of me, that's going to be confusing. Get all my pens out, why not? Why not? So this one is the usual angle between A and B. And this gives me the direction. And the direction is from the right-hand rule. Now, yes?
Can you divide vectors?
No. You can't divide vectors. But you can multiply them two different ways.
Okay.
I guess if you say you can multiply them like this and get another vector, in theory you work out what vector you multiply that one by to get this one. We're not going there. No. We don't define division for vectors. What do I mean by the right-hand rule? Hold up your right hand. A, B, N. A, B, N. You will remember that from electromagnetism, right? Motion, field, palm is the push on a positive charge in physics. You'll do that next year in physics, if you're doing physics still next year. So that tells me the direction, all right? It's a unit vector. The only thing this is contributing is the direction.
Is this A?
Yes.
Okay.
Yes. A, B, out.
Okay.
It comes out of the plane that contains A and B. So even if I start with A and B being two-dimensional, this one's going to be out of that plane. So this gives you a way to find a vector that is perpendicular to both of these. It's perpendicular to the plane that contains both those vectors. So, simple example. Wow, it really is out of ink. Okay, put that one over there, it needs more ink. 4, 7, 60 degrees. I'm going to call this one A and this one B. So then A cross B is 4 times 7 times sine 60 degrees in some direction. Well, what's sine 60?
1 over 2. 1 over 2.
Don't guess.
1 over 2.
How do you remember this?
That's funny.
Don't stop calling out.
That's something I remember.
You call out so many things and only one of them has been partly right.
There's actually one thing I was just trying to work out what that one thing was.
How do I work out sine 60 degrees? Someone other than you. I think Rain just knows it by now.
I don't know, but I know how to do it.
What do you do, Rain?
The triangle.
Which triangle?
Not the isosceles, the right angle.
So, what are its lengths?
Isn't it root 3?
1, 2, root 3. Which angle is 60?
The top one.
So sine is root 3 on 2. Opposite on hypotenuse. You
Yeah.
need to know this, you need to be good at this.
That's what I said.
No, you said 2, root 2, 1 on, 1 on.
One of them was right.
At one point you said root 3. That's the only thing you got right.
Yeah.
But you said so many other things, I'm sorry, you're not right. Okay? Guessing a million things doesn't mean you're right, or that you know it. You need to be able to work this out. Okay, 28 root 3 on 2 is 14 root 3. In which direction? A, B, into the page. Into the page. In my case, the board, but you can write page. So the cross product of these two vectors goes into the board. Yes.
Y sine 6, 1, Y sine.
Because we've already got one that's got cos.
Why?
So we can do different things with it. You will see some applications coming. It's actually because it's finding a vector normal to the plane, so it can tell us something about this angle, which is about sine, not about cos, because it's vertical out. It's the y coordinate. If you were to do this versus that. It's just the definition. This is the definition. Remember I said the dot product? This is the definition. Dot product has a cos, cross product has a sine. Then the question is, what else can we do when we learn this? What other things can we get out of it? We can get planes, we can get areas, we can get volumes using this. But it has a direction. This one is a vector. This is always a scalar, but this one is a vector.
But what is it telling you? Like,
it's telling me, you mean what's the magnitude telling me?
well, what are both things telling you? Like,
The direction is telling me the normal to the plane containing these two vectors. These might not be two-dimensional vectors. They might be in 3 dimensions. One here and one here. No, let's do it differently. One here and one here. Right, so I've got a non-90-degree angle. This is the plane, so my cross product will be this way or this way, normal to that plane. So that cross product actually tells me the direction the plane's going.
okay.
What's the scalar do?
Exactly the same as this. It's linked to the two lengths, the product of the lengths, and how close they are together. Because this one actually goes the two lengths and how far they are apart. Because it's sine, not cos. Think. Let me do the dot product for you.
Why?
A dot B, let me show you, would be 4 times 7 times cos 60 degrees, which is 28 root 3. Right? No, it's not. It's 14. It's 28 times a half, which is 14. Right? If these two get closer together, the dot product will increase. Because cos gets, if they get closer together, the angle decreases, cos gets closer to 1. But as these two get closer together, the angle decreases, sine decreases, this gets smaller.
So it's kind of the opposite?
Yes.
But why?
Because that's the way they're defined. That's how the operations are defined. This is what dot product means. This is what cross product means.
Okay.
That's the definition. Then what do we do with it? Well, because they're getting closer together, when the vectors get closer together, we can use it for things like in physics, work done, force, dot, displacement. So if I'm pushing this way, but the chair moves that way, it reduces how much work I'm doing. If the chair moves the same direction I'm pushing, I'm doing more work. Okay, the closer they are together, the bigger this number gets. Cross product is the opposite. The closer the vectors are together, the smaller sine theta gets, the smaller my cross product will get. which is where the linked area comes in. Think about, no, we're getting there. Think about this as a triangle. If these two ends are close together, it encloses a smaller area. If they're further apart, it encloses a bigger area. So the area we're going to find is going to be linked to the cross product. We'll get there very soon. This is all useful, except what if I give it to you like this? I need some different numbers. Do I really want to find the two lengths? Figure out somehow the angles of these and work out the angle between them? No, I do not. I want to be able to work this out in Cartesian form. There's a lovely formula up there. That is on your formula sheet. Ryan, oh no, I think that is on your formula sheet. Can you check?
Yeah, that is.
It is?
Yeah.
Okay.
Is it the big one, right?
Yeah, the big one. It is possible to explain why that works, but it involves matrices, which you haven't seen, but Rain has. It's actually the determinant of a matrix. Do you want me to show you how to do the matrix way, or do you want to just apply the formula straight off the formula sheet? I've got two different answers there. Okay. Let me use the formula first, and I'll do an aside from the matrix for probably two of you, right? Yeah. Okay, how do I do this? C cross D is. It's a vector. It's going to be IJK if you prefer. I'll write it that way they did. A2, B3. We're talking about the numbers here, not the J, right? So 1 times 4 minus A3, B2. -1 times -2. See, I'm getting those numbers out of that formula. A2, B3, A3, B2. Be very careful with negative signs. Next one says A3, B1, -1 times 1, minus A1, B3, 3 times 4. Last one, A1, B2. See how we're using all the options. A1, B2, 3 times -2. A2, B1, 1 times 1. So I've got 4 minus 2, 2I hat. -1 take 12, -13J hat. -6 take 1, -7K hat. This vector is normal to both of these.
What do you mean by normal? What's normal?
At right angles too. Perpendicular too.
Okay.
N for normal. Physics language. Perpendicular to both of these. And its length is this length times this length times the sine of the angle between them. Yes, you could use that to work out the angle between them, but this is going to be close. This is going to be quick. What actually does this come from? It is the determinant of this matrix. 3, 1, -1, 1, -2, 4.
You wrote 1 instead of 3
What?
in the first.
Oh, thank you. Thought I'd made a mistake, but I couldn't see it. How do I work this determinant out? We didn't actually. Oh, did we do this by hand when you?
No, that's 3 by.
Okay. To work this out, you go across one row. It's I hat times the determinant of the matrix remaining when I take out that, which is 1, -1, -2, 4, minus j hat times the matrix remaining when I take that out. 3, -1, 1, 4, plus k hat times the determinant of the matrix remaining when I take that out. 3, 1, 1, -2. And Rain, how do I work out the determinant of a 2 by 2?
You swap A and D. And
Not the inverse, the determinant.
or you times
AD
AD
minus
and
BC.
minus, yeah.
Okay? Which is going to be 4 minus 2 I hat. Minus 12, take 1, so 12 plus 1, 13 j hat. Plus, this one's going to be -6, take 1, -7 k hat. So that's where this weird and wonderful formula comes from. It's actually the determinant of a 3 by 3 matrix. You don't have to know that. What you have to be able to do is work this out tech-free. If you want, you can learn the formula off the sheet, or if you're like me, you just learn how to do a determinant of a matrix and always do that. It doesn't matter. You haven't done matrices yet. That's why they just give you a formula.